Good morning, ma'am. Myself G. Anusha from AIML department. My topic regarding AAT Tech Talk video is the generalized inverse inequalities for symmetric non-negative definite matrices. Let A be the symmetric positive definite matrix and B be the symmetric non-negative definite matrix. If the difference between them is positive, then the difference of 1 into A minus and B power minus is also positive. If A and B are all negative definite matrix, then the relationship if only the ranks of the matrices are same, that is difference of A power plus and B power plus is symmetric non-negative definite. Here where A plus is Penrose Moore's inverse of matrix of A, these were proved by Millikan and Actonis. Here Wang improved this inequality and extended his result. Bell-Megas theorem. Introduction. Let A be the symmetric positive definite matrix and B be the symmetric non-negative definite matrix. Then A power minus 1, 1 minus 1 greater than or equals to A plus B minus 1 greater than or equals to 0 if A is also symmetric, that is non-negative definite matrix, then A power plus greater than or equals to A plus B greater than or equals to 0. Then the rank of A plus B equals to rank of A. Let it be the equation 1. In equation 1, A plus is Penrose Moore's inverse matrix of A. Wang is another one. He removed this condition 1 and he obtained that A power plus greater than or equals to A plus A into A power plus into B into A power plus into whole power plus greater than or equal to 0. This equation 2 doesn't append any conditions. And equation 2 holds only for arbitrary two symmetric non-negative definite matrices. Let's take A and B are two symmetric non-negative definite matrices. If A greater than or equals to B and rank of A equals to rank of B, then B power plus greater than or equals to A greater than or equals to 0. If A greater than or equals to B and rank of A equals to rank of B, if these two conditions are satisfied, then B power plus greater than or equals to A power plus greater than or equals to 0. In this, A and B are two symmetric non-negative definite matrices. Next, a generalized inverse of A is any matrix G such that A into G into A equals to A and G into A into G equals to G. A into G whole transpose equals to AG and G into A whole transpose equals to GA. If G satisfies the I, J and so on up to Lth of 4 equations, then G is also called as the IJL inverse of A, denoted by A to the power IJL and so on up to L. To simplify this, let's take A to the power 1, 2, 3, 4 equals to A plus and A power 1 equals to A minus. In this, C of A denotes the column space of A and C perpendicular to A the orthogonal space of CA. The inequalities for the sum of matrices. We have to state two lemmas in which lemma 2.1 and 2.2 are easy and they are the basic and it is easy to prove. First, lemma 2.1, if A is symmetric, then A power plus and A into A power plus are symmetric. If A is symmetric non-negative definite, then A power plus is also a non-negative definite. Here the statement states that if A is a symmetric, then A power plus and A into A power plus are symmetric. If A is non-negative definite, then A power plus is also symmetric non-negative definite. Lemma 2.2, if A comma B two symmetric non-negative definite matrices and C is any real matrix. If A greater than or equals to B, then C transpose A into C greater than or equals to C transpose B is C. Lemma 2.3. Let A comma B are two arbitrary real matrices. Then C of B is the proper subset to C of A, that is A into A power minus into B equals to B. Let's prove that. Let A comma B two symmetric. It follows from Harvey that C of B is the proper subset to C of A, then A into A plus into B equals to B. A comma B, we know that A comma B are symmetric matrices. Then there exists matrix C such that A into C equals to B into C transpose A. Thus A into A minus into B into A minus into A equals to A into C into A minus A equals to C transpose A into A minus into A equals to B. Next, lemma 2.4. Let A comma B be two symmetric non-negative definite matrices. Then C of A is the proper subset to C of A plus B. Proof. Let B greater than or equal to 0 and A plus B greater than or equals to A. If A x transpose into A plus B into X greater than or equals to X transpose AX for arbitrary of X, if A belongs to C power perpendicular and A of A plus B, then X transpose A plus B into X equals to 0, then X transpose into A into X equals to 0, which gives X into transpose into A equals to 0. Since we know that A is a symmetric non-negative definite, that is X belongs to C perpendicular of A, so C to the power perpendicular A plus B is a subset to C orthogonal of A, that is C of A is a subset to C of A plus B. Lemma 2.5. Let A be the two symmetric and non-negative definite matrices. If rank of A plus B greater than or equals to rank of A, then C of A equals to C of A plus B. Proof. It follows from lemma 2.4 that we know that rank of A greater than or rank of A less than or equals to rank of A plus B. Since C of A is a subset to C of A plus B, if rank of A plus B greater than or equals to rank of A equals to rank of A plus B, thus C of A equals to C plus B. Theorem 2.1. Let A be the two symmetric non-negative definite matrices, then let A and B are two symmetric matrices and C is the arbitrary appropriate real square matrix. We have to prove that C. We know that A plus AC transpose into BCA power plus greater than or equal to 0. Then A plus AC transpose BCA is the symmetric non-negative definite matrices. It is obtained from lemma 2.2 and 2.4. Then C of A is the subset to C of A plus A into C transpose into B into C into A. Let it be the equation 3. And A plus A into C transpose into B into C into A equals to A into, we have to take A common here from this, and I plus C transpose B C A. Next, we get the value of C of A plus A into C transpose into B into CA is a subset to C of A. Then rank of A equals to rank of A plus A into C transpose into B into C into A. From the equations 3 and 4, we get that A power plus greater than or equals to A into C transpose BCA whole power plus. Next, corollary 2.1. This was proved by Wang. Let A and B are two symmetric non-negative definite matrices. Then A to the power plus greater than or equals to A plus A into A plus into B into A to the power plus into A whole plus greater than or equal to 0. Next theorem. Let A comma B are two symmetric non-negative definite matrices. Then A plus greater than or equals to A plus A into A to the power minus into B into B to the power minus into A whole to the power plus greater than or equal to 0. Here A minus are symmetric inverse of A. Next proof. The result follows from theorem 2.1, noting that A to the power minus whole transpose is the equation 1 inverse of A, that is A to the power minus whole transpose, that it is a symmetric A inverse, since A into A inverse of whole transpose equals to A into A minus into A into this is whole transpose equals to A. Here A into A minus whole transpose into A equals to A into A transpose into A whole transpose equals to A. Next, remark 2.1. It is obvious that the other symmetric inverses G equals to A to the power 1 comma 2, A to the power 1 comma 3, A to the power 1 comma 3 and A to the power 1 2 3 and A to the power 1 2 3 4, A to the power 1 3 4 of A all satisfies this A all satisfies that A to the power plus greater than or equals to A plus in A plus A into G into B into G into A whole to the power plus greater than or equals to 0. Next one, let take A and B are two symmetric non-negative definite matrices. If A into C transpose into B into C into A equals to B, if these is equals to B, then A to the power plus greater than or equals to A plus B whole plus greater than or equal to 0. Here C is the arbitrary appropriate real square matrix. Next one, let A be symmetric positive definite matrix, then B is greater than or equal to 0 and A inverse greater than or equals to A plus B whole inverse greater than 0. Next one, let A comma B be two symmetric non-negative definite matrices if A into A to the power plus equals to B into B to the power plus, then A into the power plus greater than or equals to A plus B whole to the power plus greater than or equal to 0. Next one, corollary 2.6. Let take A and B are two symmetric non-negative definite matrices. If C of B is a subset to C of A, then A to the power plus A plus B to the power plus greater than or equal to 0. Next, if A plus B are two symmetric non-negative definite matrices, if C of A plus B is a subset to C of A, then A to the power plus greater than or equal to A plus B whole to the power plus greater than or equal to 0. Next one, if A and B are two symmetric non-negative definite matrices, if rank of A plus B equals to rank of A, then A plus greater than or equals to A plus B whole to the power plus greater than or equals to 0. If the inequalities were the product of sum of matrices. If A and A comma B are two symmetric non-negative matrices and A greater than or equals to B, then C of B is a subset to C of A. And if A comma B are two symmetric non-negative definite matrices, if A greater than or equals to B, then B plus greater than or equals to B into B plus into A into B plus into B greater than or equal to 0. Here in these first two, we see that both A and B are two symmetric non-negative matrices. If A greater than or equals to B, we get C of B is subset to C of A, and also B into the power plus greater than or equals to B into B plus into A, B plus into B whole to the power plus greater than or equals to 0. This second one we have to prove. This we know that B into B power plus into A into B power plus into B whole to the power plus greater than or equals to 0, and B into B to the power plus into A into A B to the power plus into B greater than or equals to B into B plus into B plus into B equals to B. Here multiply with R on both sides and we get R into B plus into A B plus into B greater than or equals to R of B. And since we get this equation and we have to follow the subset rule, so C into B plus A B plus B is the subset to C of B, hence B plus greater than or equals to B into B plus A B plus into B whole to the power plus. Next, let A comma B be two symmetric non-negative definite matrices. If A greater than or equals to B and rank of A equals to rank of B, then B to the power plus greater than or equals to A to the power plus greater than or equals to 0. Proof. We know that C of A equals to C of B, then rank of A equals to rank of B. Thus B into B plus into A into AB plus B equals to A. This we get from the lemma 2.3. Next, let A comma B are two symmetric non-negative definite matrices. If B plus A B plus into B greater than or equals to B, then B plus greater than or equals to B into B power plus A into A power plus into B whole to the power plus greater than or equal to 0. This is similar to 3.1. And if let A comma B are two any symmetric non-negative definite matrices, if B into C to the power T transpose ACB greater than or equals to B, then B to the power plus greater than or equals to BC transpose ACB plus greater than or equal to 0. Next one. Here I end the topic, ma'am. Thank you.